class, we are now on 6.5b. This is precipitation reactions. We are now going to be looking at reactions that cause an insoluble compound to form. But there's different types of reactions, so this one's just precipitation out of these. So as you can see here, the difference of solubilities of ionic compounds causes some very dramatic reactions. You can see this is a very pretty color. For example, aqueous lead nitrate, which is what you see here, and aqueous sodium iodide are both colorless solutions. However, if we combine these, a yellow solid immediately forms. The yellow solid is lead 2 iodide. The other product from this reaction is sodium nitrate. Those are the ions, just in ionic form, swimming in the aqueous solution above it. So we describe this reaction using this type of equation. So in which two, let me see, sorry here. Trying to make sense of, sometimes I don't understand my own writing. This type of reaction in which two aqueous solutions, and you know these are aqueous because this is where the physical states are, tells you, combine to produce a solid, there's the solid, insoluble product. This is called a precipitation reaction, where you had two solutions, think of two solutions, aqueous solutions, compounds in aqueous solutions, I should say, and they produce a solid, and what is not used will float in the solution as a leftover, in a sense, if that's how you can imagine it. So the solid product formed in the reaction is the precipitate. In the equation above, the precipitate is indicated by the S notation, and it will always have an S if it's a solid. After the chemical formula, compounds that remain in solution will always have an AQ attached to them. So precipitation reactions are examples of double displacement reactions. Remember the dancing partners? In this reaction, the two anions, which are nitrate and iodide, swap partners. And when they did that, this now produced a solid. And it doesn't have to be the anions. You can either switch the anions or you can switch the cations. Whichever one you choose, you will end up with mixed partners. Okay, so here is my slide again. I think I showed this on the previous one. This is just a breakdown because we're going to expand on what we showed on the reading the solubilities. So molecular equation is everything in total neutral formulas. So you don't see the ions, you don't see the charges, you don't see anything with it. When it's asked for being ionic form, now you split them in half. You split them with their charges and how many there are. So that's what you see. However, if one produces a solid, you leave that one intact. You will not break that up because it is, those ions came together and created a solid. So when you, that's what I'm pretty much saying here, do not separate solid, liquid, or gaseous compounds. So if it's in a gas, you leave it. If it's in a liquid, you leave it. So something like H2O, you won't separate that out if that's what's come together as the product in a solid, which we haven't really covered these in depth yet, but I'm just getting this out for you. And this is another one which we haven't really built up yet, but what it's called spectator ions, which is actually the next thing that we're going to talk about here. So the next thing we're going to talk about is spectator ions. What are spectator ions? Spectator means exactly what you hear. Think about a baseball game, Dodger game. You go, you're a spectator. You're watching the game, but you do not participate in it. You're simply watching it. That is what's happening here. And when we put these in ionic form, you can see that you have a nitrate here. You have the same nitrate on this side. You have the same sodium here, which is on this side. So basically, you could cross these out if you needed to because they have nothing to do with the actual equation that's produced a solid. So that's what spectator ions are. So that's what we're going to talk about next. So when you look at this is why it's sometimes easier to understand what's happening in a chemical reaction by putting the compounds in ionic form, because then you can actually see something visually of what's happening. Eventually you get to the point that you won't have to do that, but while you're learning it, it is easy. It's maybe harder for you to understand it, but by breaking these up and breaking them into their sections, you can isolate them away, and visually sometimes it makes more sense for some people. All right, so if we look at an ionic equation, before these solutions are mixed, each contains dissolved ions. So if we have this clear solution here of lead 2 nitrate, and we have sodium iodide, they're both in their clear solutions, because remember, if we go to the front page, that's what we have here. That's what we're looking at here. Okay, when these solutions are combined, all four ions are present in solution. So everything gets dissolved. The sodium ions become, well, they're ions, they become dissolved. The nitrate ions do, as well as the lead and the iodine. But these come together, and that forms the yellow that you see here. So all four are in the solution. So all four ions are present in solution. However, as the lead and the iodide ions encounter each other, they bind together and drop out of solution as a solid, which is a precipitate. We can write this as an ionic equation. So before the reaction, all four ions are present in solution. After the reaction, lead iodide is a solid, but the other two ions, which is what you see here, sodium and nitrate, are present in solution. In this reaction, notice that while sodium and nitrate are present, they don't actually react. They are the same before and after the reaction. These ions are called spectator ions. They are present in the precipitation reaction, but not directly involved. In a precipitation reaction, the driving force is the formation of the solid. If the solid does not form, then no reaction takes place, and you'll have just all four ions swimming in solution, and you would get aqueous, 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 and it would all be ions. So you can see the spectator ions. These match what I have here. They're spectator ions. Remember those solubilities? I told you nitrates are always soluble. If it's attached to a nitrate, it's soluble. So those are when it helps you when you understand those little few things like sodium. It's another one. Okay, so let's take a look at another one. This equation we've shown here is called a complete ionic equation. It shows all the ions present. It shows including the spectator ions. So when you do a complete ionic, it is everything. But you keep the solid intact. That's what my breakdown of my own slides were saying. It's just exactly the same thing here. Now, sometimes it's helpful to show precipitation reactions as a net ionic equation. In this type of equation, we omit the spectator ions, so you remove them, and only include the ions directly involved in the precipitation reaction. That is a net ionic equation. That's where you have to know the terminology and understand exactly what's being asked. Because if I ask for the net ionic and you give me this, it's wrong. Yes, you have the chemical reaction there, but that's not what I asked. I asked specifically for the net ionic, which only includes ions that are involved in precipitation. So you see, this is where you cross this out, cross this out, cross this out, cross out, and you circle the ones you can see, and those are the ones that you can bring down and make it into a net ionic equation. Okay, so let's summarize what we have discussed. There are three types of equations we can use to show how precipitation reactions occur. In a molecular equation, rewrite the equations for neutral compounds and use the phase symbols. You always have to have phase symbols. Let me explain. Once something's introduced to you in chemistry, you will carry it out throughout now. You cannot, same as like when you learn sig figs. We will always use sig figs. Next section, we're doing a lot of math. You're going to get more experience with sig figs than you probably ever want to. Once it's introduced, you carry it through. So now that you have physical states, you will always use physical states. So if you're writing things out, get used to putting the physical states with it. All right, so in a molecular equation, we write the equations for neutral compounds and use the phase symbols to indicate whether they are aqueous or solid. In a complete ionic equation, we show all ions present. Dissociated ions are written separately, but we show the precipitate as a compound. So we join that together. We never separate it since it's no longer in separate ion form because they came together. Finally, in a net ionic equation, we omit the spectator ions and only show the ions involved in the precipitation reaction. The solubility rules are the key to predicting precipitation reactions. If a cation and an anion can combine to form an insoluble product, a precipitation reaction will occur. So I make sure you understand what is being asked of these. Try to visualize how to break these up. For instance, if it messes you up with some, I want to point out some of these. So here is a 2. That means that you're going to have 2 potassium and 2 chloride. Remember, you multiply it this way, you multiply it with this one. Well, what about you have subscripts? Same thing. Break this up, take the charge up, but remember you have 2 of these. So you have to account for the 2, which I'm on this side. Oh, it's a solid, so sorry. Let's jump over here. Nitrate, there's 2 of them, so you have to account for the 2. Don't confuse yourself. This really is not as difficult as it may seem. It's just foreign, so it seems like it is. Visually break them up, put the charges, and then count how many. And if there is, put the 2. then you have to balance everything. So, which again, we've already gone over with this. So it may take a little while, but it's stuff that has already been introduced to you. Take your time, put the effort in, and you will find that this actually is not as difficult as it may seem if you keep putting an effort into it. Okay, so let's look at another reaction. Hold on, let me go back here. The solubility rules are the key to predicting precipitation reactions. So if you're wondering how you do that, that's where the solubility table comes in. If a cation and an anion can combine to form an insoluble product, a precipitation will occur. And precipitation reactions are there's 3 different types for double displacement or double replacement. So remember when I discussed, let's see if I even brought it up. I brought it up, but I didn't say it. Remember, a double is A, B, C, D. There's 3 different types. This is the first one. This is a precipitation reaction. So this is what we're talking about now when it comes to double displacement or double replacement reactions. So now let's look at another example. We have aqueous silver acetate is combined with aqueous barium chloride. A white precipitate forms. Write balanced complete ionic, net ionic, and molecular equations to show the reaction that takes place. Include phase symbols. So the first thing I would tell you to do is pull out all the information that you can identify. Pull it all out so that you understand what you're looking at. Don't get confused. The number one thing about chemistry is it is a self-esteem breaker. You will never feel confident in it. Most of my students don't. It doesn't mean you don't know it. You just somehow, I don't know what it is with chemistry. It really makes you it makes you question yourself. You have the skills. You do. Just take a deep breath. Pull out what you know. And the first thing I do is if I get a paragraph like that, I write the compound above it. I write the compound where I can find it. I write the physical state out. Because if I can write those out, then it makes it easier to pull them out. And once I do, that's the first step. You have to get the compounds right. And then from there, you can do the rest of the equations. I always tend to write everything above whatever the wording is. I've always done that. I don't know even where I got that from. Okay, so in this case, I would write these out, the compounds. I wouldn't even write them in ionic form yet. I would just write the compounds and the physical states. But after I have identified them, now I know that I need to identify the ions. So the silver acetate solution contains silver ions and acetate ions. So I would write those out separately, because you're going to need to balance this out. So you're doing with the bare skeleton of putting this together. The barium chloride contains barium ions and it contains chloride ions. Okay, so it's telling you that these are aqueous. That's the nice thing is that you don't even have to look at a chart to do just the solubility. It's telling you that. It's also telling you what formed in a precipitate. So you don't even have to worry about that. Let me see. Actually, I may have jumped ahead. Aqueous barium chloride. No. A white precipitate forms. So you do have to figure out what the solid is. I spoke too soon. You will have to look at a solubility table. But you know that you're looking for something that does form a precipitate. Okay, so based on the solubility rules, the compound formed from silver chloride ions is insoluble. So now you know what that one is. I would write that where it says white precipitate. The solid product in this reaction is silver chloride. So you write a balanced, so if it makes it easier for you, and honestly, I think it would be easier if you write a balanced equation first. So I would honestly do a molecular equation first, because this is just too much for me. And I've been doing chemistry a long time, and even this is too much for me. So I would start with a molecular equation first. So I would start with this one and put this together. Because this now, once you get this, you can now separate into ionic. So once you get the molecular, then you can put it in complete ionic form. Why do I think this is easier? Because balancing, these are grouped up. Here it's separate. You have to make sure every single thing is balanced out separately. Where when it's here, you can actually say, okay, barium is here, but I have 2 of these. Instead of going, okay, I have 2 here, I have to make sure I have 2 over here. That's just too much for me. And I don't do groups. I break them up into the actual elements. So that's why for me, I didn't learn how to do them in groups. So I would do the molecular equation. That's just my suggestion. And then tackle complete ionic and net ionic equation. Okay, so once you balance that, then you can break it down and do the complete ionic equation. And then what do you do to get the net ionic? It's quite simple. You simply remove the spectator ions. So here's a spectator ion because it's here, and here's a spectator ion because it's here. So what's in red would be the net ionic equation. And that's, you've solved this out by understanding what's written, write it out, take your time, then look at solubility to find the solid, which is what you found here. Put it together. I'm not going to tell you guys how to do that, but I would do the molecular equation first and then break it down to the complete ionic, and then figure out we already know what the solid is, so we know which ones would be the spectator. Put in the net ionic equation. Okay, so I gave you a bunch of samples from my other slides for another class to help you understand here. So I'm just going to go through these really quickly because I think these are something that you need to go through. Like I said, it takes an effort and it takes time, but once you learn how to do this, you won't forget it. It stays with you. So magnesium chloride dissolves in water. Write a molecular equation and ionic equation. So in this case, actually, no, I think this is part of their slides. This goes from solid to liquid, right? So it goes to aqueous. So I don't like this one. I don't like this one because we haven't really introduced water, and all of a sudden, yeah, they gave you this. I didn't do this one. But let's break this down. Now that they gave it, let's discuss it. Magnesium chloride dissolves in water. So what it's saying is that we had magnesium chloride, and it's been placed into water. Now, I already caught something I don't like about this, because if magnesium chloride is a solid, then this should be a solid, and these would be aqueous. So they gave me this slide, and I think this is a mistake. This should be a solid because that's what it's saying. It dissolves in water. So why is it an aqueous already? It's not going to be. It's dissolving into water. So this here is wrong. It should be a solid because what we're showing is the transgression of it going from solid to liquid. I hope that makes sense. So then what does it want? It wants a molecular equation. So I pretty much wouldn't have put this like this. I would have left it as solid and then broken it down into just this here and removed the water out of this completely, because when it's an aqueous, that's already understood to be in water. I would try to avoid something like this for you. Remember, I don't pick your homework questions. So this is, I don't have any say in what's given to you as a student. Ionic equation, this is exactly what I would leave it as, and I would change it to molecular and put a solid here. And that's how I would leave this, because aqueous pretty much, I feel like this is just repeating itself. It's already in an aqueous solution. Okay, so aqueous potassium chloride and aqueous silver nitrate react to form a solid silver chloride and aqueous potassium nitrate. Write a molecular, ionic, and net ionic for this. So I'm just going to put this out here for you. This is one I would suggest you look at this slide first, try to put it together, and then compare it and see if you match up with what it is here. I believe this is one of my own slides, so this one is not. This one came with it. I don't like this one. If I had really paid attention, I would have fixed this. This one seems to match more of what I would do. All right, so identify the precipitate that will form in the following reactions. This is one of theirs, because this is that ugly table and I don't like. But it doesn't matter. It wants you to complete this. So you're going to have to visually switch these over. So switch them over and then balance them out. And then once you're done with balancing, don't jump to look at this yet. I honestly don't think you should. Balance the equations out and then solve what it's asking for. So in this case, what it's saying is that put the precipitate first, if there is one, and then the aqueous over here. So let's see what happens here. I'm going to do the first one. We have sodium. Anything with sodium is aqueous. So anything that's going to be attached here. So if we switch these, that's going to go with sodium chloride. We already know that's going to dissolve. But now we have barium carbonate. So we don't have any carbonates up here. So that means that that is a solid. So I'm just going to jump ahead and show you how to put these. So that's what it means by precipitate and other, is it wants all the solids listed first, and anything that's in ion swimming in solution is next. But make sure you balance these out. Okay, describe the reaction of lead 2 chlorate with calcium iodide using the molecular. So this is asking for, it's giving you your AB plus CD, put them together, balance it, then look at the physical states, and then you can go on from there, from the ionic and net ionic. That's why I always do the molecular first. Oh, this moved. I would not have had this so jumbled. Okay, but it's giving you everything here. Sorry about that. It moved on me. So you get the molecular here. You do see that there's a solid. So let's see if we understand this. This is a halide, but it's attached to lead. So that's where the solid comes from. Now we're going to break it all up except for the solid. And then we remove all the spectator ions and give just the actual equation, which is really easy because it's whatever creates the solid. Everything else is out. Iron 2 carbonate is insoluble in water, so it's telling you it's not going to dissolve. Propose 2 aqueous solutions that could combine to form this compound in a precipitation reaction, right? A balanced equation. So basically what it's showing you is it's telling you that this is the product. This is on the other side of the arrow. So put 2 things together that will cause these to come together and create that solid. So in this case, we could do potassium carbonate. Carbonate would attach to the iron, and that thereby causing, giving you the solid. And then you can, the other ions that are created are just in solution. So this is kind of giving you a freedom based on the solubility chart of you picking things, putting them together, creating the reaction, and knowing that this is going to create a solid and the other 2 are just going to swim in the solution. Okay, in this reaction, what does the symbol aqueous after copper 2 chloride mean? So AQ means aqueous. It means water. It's dissolved in water. So it's A. In this reaction, copper 2 carbonate is the, if we look here, we can see it's an S. So it's precipitate. What is the net ionic equation for this reaction? So I'm just going to jump to the answer because this is something you're going to have to learn how to do. And the beakers below show aqueous solutions with, I put a lot of examples on here for you. Show aqueous solutions with dissolved ions. If we combine these solutions, what precipitate will form? So when you look, you can check and see which ones of these are going to form. If you can visually match these together, and you're going to see it's going to be iron 2 hydroxide. Which 2 products will form in this reaction? So this is where you switch dancing partners, and then you look at the solubility chart, and I'm just going to give you that information. Summary of precipitation reactions. So let's summarize the ideas related to solubility and how they relate. First, soluble ionic compounds dissociate in water. Some ionic compounds are insoluble in water. Solubility rules predict the solubility. So that's where you have to look at those. When 2 aqueous solutions combine to produce an insoluble product, a precipitation reaction occurs. We describe reactions in solution 3 ways. We use molecular equations to show the ions as compounds, neutral compounds, or complete ionic equations that show the associated ions, and the last one is net ionic, which show only the ions directly involved in bonding. Predicting precipitation reactions and writing equations requires study and practice. This is where you need to really become familiar, and I'm giving you all the information, but trust me, it doesn't stay, and you don't learn it if you don't actually work and do the examples. But so far from what I've looked in this class, I have a really good class, and I think you guys will handle this